Dear students, welcome back to e-learning class. Myself Santosh VJ. Dear students, in previous class we discussed about the compaction process for the PM parts. Today is my sixth video class for the module 3. Today topic is that sintering process for PM parts. So let us discuss the sintering techniques for the PM products. Dear students, listen carefully. Dear students, as per the today plan, now we will discuss the sintering process. Sintering is the last process of making the powder particles in powder metal technology. The sintering is a process by which a powder compact is transferred to a strong dense ceramic body upon heating, which means the process of heating the compacted powders to make a densification and green strength of the compacted powder. And sintering is also could eliminate the most force in porous green body and compress the residual force and bring the grain growth and improve the bonding among all the grains. So this phenomenon is called as a sintering process. Now we will discuss why do we need the sintering process. Definitely, dear students, the principal goal of sintering is the reduction of compact porosity. Sometimes in initial space between the compacted grains of ceramics are called as a odes that differentiate them from the isolated space, which means the pores which occurs in the final stage of sintering. The sintering process is usually accompanied by other changes within the material, some desirable and some undesirable properties. The largest changes occurs in the sintering process or while sintering. Some desirable properties which we can discuss here. Here we can take strength and elastic modulus, hardness and fracture toughness will be improved, electrical and thermal conductivity will be improved, permeability to gases and liquids, average grain number, size and shape, distribution of grain size and shape, average pore size and shape, distribution of pore size and shape, chemical composition and crystal structure. Let's coming to the next concept. What happens during the sintering? Exactly, the atomic diffusion takes place and the welded areas formed during the compaction grow until eventually they may be lost completely. The recrystallization and grain growth may follow, and the pores tend to become rounded, and the total porosity as a percentage of the whole volume tends to decreases. In this pressing operation, the powder particles are brought together and deform at the point of contact. At elevated temperature, the sintering temperature of the atoms can be moved more easily and quickly migrated along the particle surface, which means the technical term is called diffusion. The metals consist of crystallites. At the sintering temperature, new crystallites form at the point of contact so that the original interparticle boundaries disappear or become a recognizable merge as a grain boundary. So this term is called as a recrystallization process. This is what happening while sintering the compacted particles. Yes, as we can see the image, dear students, the image left image what we can see, this is the before sintering. What we can observing the second image is after sintering. Here the spherical shape of particles, once they are sintered, now the spherical particles are becomes like this. Now in between these two, in these four atoms, at the middle, this is the point of contact, this is called as a pore, and this is called as a neck, and In between the two lines there is a boundary line that is called as a grain boundary, or also called as a GB, grain boundary lines. So now we will discuss the types of sintering processes. Number one, conventional sintering process, or it is also called as a traditional sintering process. The dense nano microstructure ceramic materials are usually obtained by pressing and conventional sintering of nano powders using pressure assisted methods such as hot pressing and hot isostatic pressing. And second is that advanced sintering process, can also called as a modern sintering processes, show great potential in ceramic processing, overcomes the problems of grain growth. And third one is a high frequency induction heat sintering. It is similar to hot pressing, which is carried out in a graphite die, but heating is accomplished by a source of high frequency electricity to drive a large alternating current through a coil. This coil is known as the work coil. The passage of current through this coil generates a very intense and rapidly changing magnetic field in the space within the work coil. So due to this reason, the, the enough temperature will be generated that could be heat the compacted particles. Yes, let us discuss some important parameters in sintering process. Some parameters such as sintering temperature, applied pressure, average particle size, and temperature, atmosphere can be controlled with a sufficient accuracy. And others such as powder characteristics and particle packing are more difficult to control but have a significant effect on sintering. Yes, let us discuss conventional press and sintering. The after metallic powders have been produced, the conventional PM sequence is consisting of number one is the blending and mixing as we discussed in previous class, and compaction as we discussed in previous class, pressing into a desired shape. And now we will discussing the sintering, the heating to a temperature below melting point to cause the solid state bonding of particles and strengthening of a part. In addition, the secondary operations are sometimes performed to improve the dimensional accuracy, increase the density, and for other reasons. So coming to the uh, other types of sinterings which are comes under the conventional process. Number one, solid state sintering. Now only a solid phases are present at the sinter temperature. And liquid phase sintering, the small amounts of liquid phase are present during the sintering. And reactive sintering, the particles react with each other to a new product or new product phase will be formed. Yes, as we can see the image, dear students, here we have two images. One is a solid state sintering image, other one is a liquid phase sintering image. What we can see in the left side image is indicated that solid state sintering processes, and what we can see the right side image is indicated that liquid phase sintering process. As now we will discuss the concept of liquid phase sintering process. The grain boundaries wetting breaks these polycrystalline particles into a single crystal. What we can see, the first image is a polycrystalline particles breaks the this polycrystalline particle into a single crystal particles in the initial stage. What we can see in the image 2, this is the single crystal particles. The stages of liquid phase sintering, these single crystals particles then spheroidize and coarsen at what we can see in the image 3. So it is look like an spheroidal and coarsen structure. Let us discuss some importance of sintering process. It imparts the strength and densification and dimensional control, decrease the free energy due to decrease the surface area, and zero point 0.7 to zero point 0.9 melting temperature of the major constituents. Metal powder below the melting temperature with or without the application of external pressure to form it to a dense material by interparticle bonding. A progressive transition without melting, which are diffusion of particles to particles, formation of grain boundary, and closing odes present in the green compact. Let us discuss the loose sintering. What exactly is the loose sintering, how it works, and what is the mechanism of loose sintering. The mechanical vibration in the mold followed by the heating to sintering temperature. This process is simple and low cost. Porosity varies from 50% to 90%, not suitable for the complex parts because of the reason difficulty of part removal, flow characteristics of powder, shrinkage during the sintering, and the dye materials which we can use in the loose sintering: carbide materials, graphite, stainless steel, and cast iron materials which we use for making a dyes, and also poor dimensional accuracy. We could achieve the poor dimensional accuracy. Let's come to the point. Changes during the sintering. Dear students, uh, there may be a possibility to uh, some changes will happens during the sintering, which are dimensional changes, chemical changes, electrical property changes, phase changes, relief of internal stress, and some alloying changes maybe happens while the sintering the process. Dear students, what we can see in here, the table. The table is consisting of the type of the powder and their sintering temperature and sintering time. As we can see, the first example is aluminum and its alloys in type of material. Their sintering temperature is around about 370 to 520 degrees Celsius, and sintering time is around about 24 hours. So called it is an age hardening or age sintering. So second example is copper and its alloys. The sintering temperature is around about 700 to 900 degrees Celsius, and the sintering time is around about 30 minutes. Third example is an iron. Sintering temperature around about 1025 to 1200 degrees Celsius, and sintering time is around about 30 minutes. And next example is a stainless steel. The sintering temperature is around about uh, 1180 degrees Celsius, and sintering time is around about 20 to 40 minutes. The tungsten carbide materials, the sintering temperature is around about 1480 degrees Celsius, and sintering time is around about 20 to 40 minutes. So here one more new material is a nickel. Sintering temperature is around about 1000 degrees Celsius to 1150 degrees Celsius, and sintering time is around about 30 to 45 minutes. And let's coming to the sintering sequence. How the sintering sequence is begins, dear students. Let us discuss through this image. What we can see, the image is indicating that how the sequence is begins in sintering process. So as we can see, the image one is a green compact, second image is indicate that neck formation, and third one is the pore size reduced, and fourth one is pulley sinter structure. The sintering on microscopic scale, the particle bonding is initiated at a contact point. As we can see, this is the green compact, and contact points grow into a necks, which is called as neck formation, what we can see in the second image. The pores between the particles are reduced in size, that could we can see from the image 3, that is called pore size reduced. The grain boundaries developed between the particles in place of the neck region, that is what we can see from the image 4, that is called full sintered image. Now we will discuss the sintering mechanisms. There are two sintering mechanisms. One is an adhesion mechanism, another one is material transport mechanism. Let us discuss one by one. Now coming to the adhesion mechanism. The adhesion mechanism, which we have some basic steps in adhesion mechanism: elementary bonding process, no material transport, a major contributor in initial stage of sintering process. In material transport mechanisms, we will discuss the recovery and recrystallization, plastic or viscous flow, evaporation and condensation, volume diffusion, surface diffusion, as well grain boundary diffusion mechanisms. All these mechanisms depends on powder materials, its characteristics, sintering temperature and atmosphere. Now we will discuss number 1, recovery and recrystallization. In recovery and recrystallization, the small displacement of atoms will be happens and observed in the powders having a severe lattice distortion due to a grain growth which occurs along with densification. The stress removal promotes the mutual bonding of powders. Coming to the viscous flow, in viscous flow, displacement of atoms over a large distance due to application of external pressure, the atoms flow under stress. Assuming total surface tension of all the pores is equal to the external pressure applied, and it is a slow process. And evaporation and condensation method, dear students, now we will discuss the evaporation and condensation mechanism. So not usually found in metal powders, exception of chromium and NaCl. The material transport through a gas phase, the evaporation of materials from surface of the spheres and condensation in the neck region. As we can see the image in the condensation in the neck region, higher vapor pressure at convex surface and neck growth without shrinkage or densification. And coming to the volume diffusion mechanism, the most important mechanism is volume diffusion mechanism, dear students. Here the atomic movement into vacant lattice sites, the vacancy gradient occurs between neck area and interior of the system, distortion and undisturbed lattice, particle centers and midpoint of contact with adjacent particles. The vacancy diffusion from the neck area, the atom diffusion is opposite direction producing welding effect, which is governed by the geometrical arrangement of powder particles, the type of vacancy sources and sinks. The vacancy sources means the smaller pores and concave surfaces. Vacancy sink means a large pores, grain boundaries, flat or convex surfaces occurs at high temperature. Let us discuss this surface diffusion mechanism. The surface diffusion mechanism, in this mechanism, the movement of atoms on external surfaces, the exchange of surface atoms and surface vacancies, and which have a responsibility for neck formation and significant for sintering fine powders at a temperature is less than that of volume diffusion, and the shrinkage will be occurs. The grain boundary diffusion mechanism. In grain boundary diffusion mechanism, the grain boundary formed between the adjacent particles in the original stress mass. The vacancies are moving along with the grain boundary to external surfaces, which is the last stage of a sintering process, and also it could eliminate of isolated force and atoms from the external surfaces or locations along the grain boundary will diffuse towards the interior, and this promotes the neck formation or neck growth and rounding or shrinkage of the pore, and also to found more effective with decreasing sintering temperature. Now let us discuss the pre-sintering concept. The PM parts will be a hard after sintering process. So machining will be difficult for such kinds of PM parts. Due to that reason, the parts are pre-sintered at low temperature than the sintering temperature, which provides the adequate strength for handling and machining the PM parts. After machining also sintering is done, and drilling is usually carried out in this method. The pre-sintering is removes the lubricants and powders. Yes, now coming to the next concept is the sintering atmosphere. Yes, is very important. The sintering atmosphere selection is depends on the characteristics of material, property desired in the sintered product, and changes occurring prior to sintering, which are reaction of constituents among each other, the reaction of atmosphere with the material to be sintered, the reaction of atmosphere with the surface, so with the furnace refractories. The sintering atmosphere, the main functions of the sintering atmosphere, which must prevent the oxidation on the metal surface at the sintering temperature, and which must avoid the carburizing and decarburizing reactions and nitriding conditions in certain metals, and which must have a tendency to reduce the surface film such as oxides on powder particles, and which must not contaminate the metal powders compact at the sintering temperature. Now, types of sintering atmospheres. Number one, reducing temperatures, which we can take here mainly the dry hydrogen or dissociated NH3, and one process, exothermic process and endothermic processes, which we can take here. The endothermic or exothermic atmosphere having a low or medium carbon potential, but endothermic atmosphere is enriched with the hydrocarbon gases to produce a carburizing atmosphere, and other atmosphere is natural atmosphere, and final one is oxidizing atmosphere. Let us discuss some advantages of sintering process. The stabilization of the details of repetitive operations by control of grain size in the input stages. The absence of segregated particles and inclusions as often occurs in melt process. No requirements for the deformation to produce the directional elongation of the tails. Yes, now we will discuss the advantages due to the particular properties of sintered components. Number one, by achieving up to 95% density, the mechanical and physical properties are comparable with the cast materials, and in certain cases with the wrought materials. In certain case, 99.9% dense structure can be obtained. And second one, the plating is also possible directly at 90% density and above and after impregnation of pores at low density. And third one is a damping out of vibrations and noise property with a controlled residual porosity. And fourth one is ability to retain the lubricants such as lead, graphite and oil, and giving a less wear and longer life to the bearing components. And fifth one is that achieving a close control of porosity to give a specified balance between the strength and lubrication properties. Let us discuss the application of PM products with examples. The mostly automobile components, for example, ferrous powders is more than 70%, which we can use for the automobile applications. And automotive components such as connecting rods, bearing cap, transmission gear, and etc. In US, more than 70% of Paris powders which are used to produce the PM components. Some electrical equipments and magnetic equipments and welding electrodes, tungsten filaments, electrical contacts, some hard magnets and soft magnets. Hard magnets such as aluminum, nickel, and cobalt alloy, and tin and cobalt alloy, and niobium, iron, and boron alloy, which are the hard magnets, and soft magnets such as iron, alloy, cobalt basis alloys are soft magnets. For aerospace applications, which we can possible to make us super alloys for the turbine discs, high strength aluminum alloys 7090 and 7091, and titanium alloys which we can use. Some medical applications which we can use for the uh, surgical equipments and dental applications, for porous orthopedic implants and dental amalgam etc. In military applications mainly such as kinetic energy, projectiles, missile components, and etc. And other applications, porous filters, bearings, found metals, and composites. Okay, dear students, now we will discuss some high-tech applications of PM products. These components are used in air and spacecraft, heavily and heavy machinery, computers, and automobiles, and etc. The applications which are anti-friction products, friction products, filters, electrical contacts, sliding electrical contacts, very hard magnets as we can see the previous, and soft magnets, refractory material products, hard and wear resistance tools, ferrous and non-ferrous structure parts. Now coming to the other heavy structured applications of PM products: gears, bearings, sprockets, fasteners, and electrical contacts as we can discuss earlier, cutting tools, and various machinery parts. When produced in large quantities, gears and bearings are ideal for PM because the geometry is defined into two dimensions. There is a need for a porosity in the parts to serve as a reservoir of lubricant. Yes, dear students, which is a collection of powder metallurgy parts. As we can see, the image is some engine components, some automotive engine components, which is made by the PM techniques. And here we have some type of gear which is also made by PM technique. Here some pressure valves and some other ring type of some pressure nozzle rings, which are all made by the PM parts. And here we have a human hair trimmer which is also made by PM product, a PM technique. Yes, dear students, so here we have two images on the slide. This is the first image what we can see from the left side. This is the powder metal transmission gear. This is the kind of the spur gear which is made by the powder metallurgy technique. The warm compaction method with the 1650 ton press. The teeth are molded near net shape. No machining is required. 30% of cost saving over the original forged part. Dear students, as we can see here, there are two connecting rods. The left side connecting rod is made by the forging and the right side connecting rod is made by the PM techniques. Let's see the difference between the both the connecting rods. Okay, now dear friends, what we can see in the image is are the so medical applications or medical surgical equipments or surgical instruments and dental implants for the human body. These are the medical applications. Now coming to the other applications of the PMs: gear manufacturing, cams, cranes, what we can see the all the engine components, uh, cranks, bearings, roller bearing cases, housings, light bulb tungsten filaments, sprinkler mechanisms, cemented carbide cutting tools, electrical contacts, brushers, and metallic coatings and metal to glass seal. Yes, dear students, as we can see the image A is the example of typical parts made by the PM process. These are the engine components which are made by the PM process. And as we can see the image B, dear students, the upper strip lever for a commercial sprinkler made by the PM process. These parts replace the die-cast part of the unsealed brass alloys with 60% savings. What we can see the image C, the main bearing metal powder caps for 3.8 and 3.1 liter General Motors automotive engine. Yes, dear friends, what we can see here, this uh, other examples for the PM products. The competitive with processes such as casting, forging, and machining used when melting point is too high, for example, tungsten and molybdenum. The reaction occurs at a melting, especially in zirconium, too hard to the machine. Due to this, the products are too much hard for machining purposes in a large quantity. So this is the reason the near 70% of the PM parts production is for the automotive applications because of good dimensional accuracy, controllable porosity, size range from tiny balls for ballpoint pens to parts weighing round about 100 lb. The most are around 5 lb or 5 pounds, 100 pounds to 5 pounds. This is the range between the any kinds of the range PM parts can be produced. Yes, dear students, now we will complete the model 3 in this class or in this session. The next session will be a new topic. uh, Module 2 we will discuss in the coming session, dear students. So hope you understand and this session was useful. Thank you.